name is Kyle Comerford, and I'm going to discuss the physical properties of a guitar. So on a guitar, there are three main factors that have to do with the sound that you hear while you're playing it. And those are the strings, the body, and then the air that's resonating inside of the guitar. So at any point near a source of sound in the air, there are molecules that are vibrating back and forth. And we call this phenomenon frequency. And frequency is measured by cycles per second, or we denote it as hertz, or Hz. And we discussed this in the lab that we did with the online simulation, where we could visualize the waves going back and forth on the string, and we could change the fixed end, the loose end, all the different sliders about density or frequency. And as you can see on a guitar, the strings lie between two fixed points, here and here. Now, the frequency pretty much entirely determines the pitch of the guitar. The higher the frequency, the higher the pitch, and vice versa. So the pitch of a vibrating string depends on four main things. The first being the mass of the string. So as you can see, if you look up close, the more massive strings lie up here towards the top, and the less massive strings lie down here towards the bottom. The more mass of the strings, the more slowly they vibrate, and thus the lower pitch. So on a classical guitar like this, the strings get thicker as you go from E to B to G, and get thicker up here as you go from D to A to E. The second factor of the frequency is the tension that you're changing on the string. So when you tune a guitar, and here your tuner's up here, as you go higher, you're putting more tension on the string, which gives you a higher frequency or a higher sound. As you can hear. And lower tension gives you a lower pitch. Another factor to the frequency is the length of the string that you're allowing to freely vibrate. So when you play a guitar, you're always changing your finger positions. And as you can hear, if you play a note on the lower end of the guitar, you're leaving all this free space to vibrate, you hear a lower pitch. As opposed to if you go all the way up here, you hear a higher pitch. And the last factor that determines frequency is the mode of vibration. And the mode of vibration is pretty much just, on a classical guitar like this, it defines a characteristic of how the string is allowed to oscillate back and forth. So this would be a freely vibrating system, and the oscillation is restricted to a certain characteristic of frequencies. So this would be defined as a normal mode of vibration. There's all kinds of modes of vibration with different characteristics of sound, but as far as we're concerned, a guitar has a normal mode of vibration. So the strings themselves hardly make any noise. They're pretty thin and slip relatively easily through the air without making much of a disturbance, and a sound wave is a disturbance of air. So if you played an electric guitar which doesn't have a body or the air inside of it, if you played an electric guitar without the amp, you wouldn't hear pretty much any noise at all. But it would be a lot quieter at least. But on an acoustic guitar, it is the vibrations of the bridge and the body that cause the noise that we hear. And the vibration is pretty much transferred from the bridge and the saddle to the top plate of the guitar. So to talk about the plate, or the body of the guitar, you have your top plate, as I just said, and you have the side and back plates. The side and back plates aren't as important because while you're playing, they're fixed to your body, so there's not that much room for them to vibrate. The front plate is the most important the most important factor to the sound that you hear. So the body serves to transmit vibration from the bridge into the air around it. And for this, it needs a relatively large surface area, so it could push a reasonable amount of air back and forth. So that's why you have such a large area in the body on the front plate. Now behind the front plate are braces that help to control the vibration and also help to keep the front plate nice and flat. So to talk about the air inside of the guitar, if I pluck a string here and put my ear up to it, I can hear it resonating back and forth. And you can associate this with blowing air across the top of a bottle. So the sound that you hear is pretty much the air resonating. And this effect is known as the Helmholtz resonance. And it's pretty much due to the air around the sound hole that's oscillating. So air is springy, and when you compress it, its pressure increases. So just pretend that there's a lump of air sitting here around the sound hole. So if this moves into the body at the small distance from the strings, between, as you can see, the very small distance between the strings and the sound hole. So if the air moves into the sound hole, it gets compressed, and that pressure drives this lump of air out. But when it gets to its original position, its momentum takes it outside of the body at a small distance, which rarefies the air inside of the body and then sucks the lump of air back in, thus causing the vibration, thus causing the sound that we hear while we play our guitar. So that pretty much is how a guitar works and its physical properties, and that's why we hear the sounds that we hear while we play it.